Okay. Hello, everyone. Welcome to our, is this fifth session? It is fifth session, isn't it? Okay. I'm going to keep saying this because I'm still surprised we've done 5 sessions, but you don't have to listen to that part. I'm just going to pat ourselves on the back, I guess. Anyways, so this is the attendance tracker. So if you haven't done this, please do so right now. We'll also show it at the end again as before, so you can see this again. But I'm going to go back to the first slide for today. So today we're going to introduce you to some AI models and some of the applications. And I understand that's a big mouthful, and I don't know how Golnaz is going to do this in 1 hour, but I have trust in her abilities. No pressure. So we'll see how that goes, but it's going to be mostly rapid fire going through some of these models. And if you need more information, we can provide more resources, and you can kind of learn these on your own as well if you'd like. If there's a lot more, I guess, interest, we can provide more resources ourselves as well in terms of extra workshops. So if that's something you're interested in, come and talk to us or email us. With that, I will pass it on to Golnaz, who is a master's student at the Department of Computing Science, or is it the Computing Science Department? Is it Computing Science Department? Okay. I get confusing. Well, okay. I seriously am confused at this point with whether it's Department of Computing Science or Computing Science Department, or even Computer Science. Anyways, so I'll pass it on to Golnaz, and she'll tell you about the AI models and applications in medicine. There you go.
Hello and good afternoon. Today we're going to talk about some AI models and their applications in medicine. So as Ehsan said, it's going to be a constant flow of information about different models and how they work or what problems they solve and what their pros and cons are. And the goal of this presentation is for you to become familiar with these models. So the goal is not for you to be able to know every detail about each model or be able to implement them, but the goal is that when you read a paper and you see that they've written, we've used this model for classification, and these are the features, and this is the accuracy that we gained. You know what that model is, what a classification problem is, and what does it mean when they've calculated the accuracy, and they're reporting that to us. So with this information, let me provide an outline for this lecture. First, we're going to talk about some general terms that we hear in AI, like AI, machine learning, deep learning. And we're going to talk about different problems that AI tries to solve, like supervised learning problems or unsupervised learning problems. And specifically, we're going to talk about problems that are more widely used in medicine, such as classification and regression. And then we're going to introduce the models. We're going to talk about decision tree, k-nearest neighbors, linear regression, logistic regression, neural networks, and convolutional neural networks. So let's start with artificial intelligence. So this is a general term, and it's broadly used with different meanings. But in general, we can say that AI, or artificial intelligence, is intelligence exhibited by machine or software. And more specifically, machine learning is a subcategory of AI, which introduces algorithms that learn from data, and they can improve automatically through the experience they gain learning from data. And to be even more specific, deep learning refers to the models that are inspired by the brain's neural networks. And deep learning models usually consist of multiple layers of calculation, so that there is a model and you give it an input and you expect an output from it. So with this information, we say that we want to build a model to solve the problem. But what does that exactly mean? It means that we have a bunch of data. So we have a data set, and the data set contains some inputs, which is denoted by X, and some outputs, which is denoted by Y. And there are many samples of the data that we want in our data set. And the model gets input, gets features as the input, and provides us with an output. And we want to build a model that can learn based on these data. And after the training phase, after the model has learned, we want the model to be able to predict unseen data, predict Y for an unseen X. It means we want the model to generalize well on unseen data. And an example for inputs for a model can be the age of a person, the sex of a person, and if they've had chest pain or not, or the value of their blood pressure. And the output can be if there's a risk for a heart disease for them or not. So this is the general idea of a machine learning model and how it works. So machine learning models can solve different problems. These problems can be supervised learning problems, unsupervised learning problems, or reinforcement learning. So this is one of the divisions of different problems that machine learning models try to solve. In a supervised learning problem, the training data is labeled. It means that we know the ground truth. We know for each sample, for example, in the previous example, we know for each sample if the person is likely to have a heart disease or not. And the algorithm is given this ground truth, and the algorithm knows the right answers during the training phase. And this way, the model is trained. An example for supervised learning problems can be classification or regression problems that we will dive into deeper later. Another set of problems that machine learning models try to solve is unsupervised learning, where data is unlabeled, so we don't know the ground truth. So what we try to do is to find and extract some patterns from the data. So we try to find, for example, clusters in the data where each member of the cluster is more similar to the other members of that cluster compared to other clusters. An example of this problem, this unsupervised learning problem in medicine, can be answering this question that, is there a pattern linking these two diseases to these factors or not? And another set of problems in machine learning is reinforcement learning problems, where the problem is modeled as the interaction between an agent and an environment, and the goal is for the agent to learn through experience and through its interaction with the environment to solve the problem. So we said that there are classification problems and regression problems as supervised learning problems, but let's dive deeper into that and let's see what exactly that means. So our goal is to, when we have a machine learning model, our goal is to predict a value as an output. And in a regression problem, this value can be a continuous value. So we want to predict a continuous value as our output. The example can be we want to predict the number of new COVID cases in the next month. So we have a time series problem where we know the pattern in the previous months. And based on that data as an input, we want to predict the future. We want to predict the number of new cases in the future. So this is an example of a regression problem in medicine. For classification problems, we aim to predict a discrete value. So an example can be, we have the sound of coughing as the input to the model, and based on input, we want to predict if the person has COVID or not. So the output is either 0 or 1, which is a discrete value, and we want to classify if the person has COVID or not. So and we say that models learn from data, so we need to know more about data and be more specific about what kind of data we feed to our model as an input, or we expect the model as an output. The data can be categorical or numerical, and for categorical, it can be binary, nominal, or ordinal. For binary, an example can be 0 or 1, yes or no, like if the person has COVID or not, if there is a fracture or not, if there is a heart attack or not. For nominal, it can be A, B, C, which can be different types of tumors or other things. For ordinal, it can be different values like 1, 2, 3, which can represent different stages of an illness, like mild, moderate, or severe. And for numerical, data can be discrete, like the number of comorbidities, and it can be continuous, like the value of something that we have measured in a test. So knowing this information and being more specific about what kind of data we're working with can help us design better models. And before jumping in to the introduction to different models, it's worth to provide a brief timeline of machine learning models. So in 1950s, the term machine learning was coined, and after that, some simple models were introduced. But because of the lack of data and because of not having enough compute power, there was an AI winter where machine learning models or deep learning was not popular. And starting from 2000, deep learning started to emerge again, because now we have fantastic hardware and great processors and CPUs and GPUs that can give us great compute power. And on the other hand, we also have many huge data sets that we can learn from. So having this compute power and having this enormous data sets, deep learning is again back, and nowadays it's very popular, and it's a very good solution to many complex problems. So by this background, let's now visit some of these models that can help us solve the problems we talked about. Let's start with decision trees. So decision tree is a machine learning model for classification problems. And as you see in the graph, decision tree starts with some nodes and at each node, we ask a question about the data that is fed to the decision tree. Like, so we have a data and we ask if there is intersystolic noise. So, and for each possible answer, the model creates a branch. And again, in each branch, we have nodes that ask questions. And we go deep down in this model. And at the end, we have the leaves of our tree, where all the data that we have are classified as a particular group, like if the person has a prolapse or not. So this is the idea of decision tree. And we say a decision tree has learned well or is a good model when the leaves are pure, which means all the data that are classified, they come from the same class. And for checking if our tree is pure enough, we need a measure of purity. In this case, it's entropy. There are also other measures of purity, but the math is not important here. It's important. What's important here is that what we're looking for is a decision tree which produces the purest result for us. So this is the general idea of a decision tree. There are some benefits for using a decision tree. They're simple, they're easy to visualize, they're efficient to use, and they're somehow like the way that we ourselves reason about some problems. And there are also some cons for using decision trees. Like sometimes they might get overly complex, or sometimes they're unstable. If there are small changes to the data, we might need to change our tree completely to fit our data again. And also it's hard to compute the best tree, the optimal tree for our problem. One example of using decision trees in medicine can be predicting adverse drug reactions. So you can later go to the link and read the paper on it. So it was shown that predicting adverse drug reactions in patients using decision trees was effective, and it gave us good accuracy. So this is about decision trees. And now let's move on to the next model. The next model is k-nearest neighbors, and it's used for classification again. And the idea is that, let's suppose we have a data set which contains two classes, class A and class B. So we have some scene data or training data that we know the information about. We know they come from some of them come from class A and some of them come from class B. And now we have a new data that we want to classify, which is unknown to us, to which class it belongs. So the idea for k-nearest neighbors is that we find the k-nearest neighbors to that point that we want to classify, and we consider the dominant class as the class that we want to assign to the new data. So this is the general idea for k-nearest neighbors, and the idea is simple. And for building a k-nearest neighbor, we need to have a measure of distance because we want to find the k-nearest points. So this distance, again, can be different measures. One example is Euclidean distance. Again, the formula is not important. What is important here is that we look for the nearest neighbors, and based on that, we classify the data. There are some considerations when using k-nearest neighbors as a classifier. One consideration is that the choice of k matters. It means that we need to choose k wisely based on the problem that we're trying to solve. Like in the picture, as you see, when we choose k as small values, what happens is that we get a very curvy line as the decision boundary between the two classes, because it is going to be very detailed, and each point is classified just based on one neighbor or just based on a few neighbors. But as we increase the value of k, the model gets more simple, so the line can be more smooth, but the danger is that the model might get too simple and might not classify well at the end. So there is a trade-off, and we need to find the good value of k that prevents from overfit or underfit. So overfit is like when the model is too complicated and too adapted to the data that we had that it cannot predict well on new data. And underfit is when our model is too simple and it cannot get the complexities of the data that we have. An example for KNN application is diagnosis of heart disease based on demographic data. And again, you can go to the link later to see what they did and how a machine learning model was used for classification of heart disease data. So we talked about two classification models, decision trees and k-nearest neighbors. Let's move to a simple regression model, linear regression. So suppose we have some inputs like the features, like if imagine a data set that we have these inputs from, like if the person smokes, if the level of their cholesterol, if they have hypertension or not. So this is the input, and the output we want to predict is the risk of heart disease as a value between 1 to 10. So we have X as input and we have Y as output, and our goal is to fit a line to our data so that we can make a linear combination of the features that we have to produce the output that we want. So in linear regression, the goal is to learn a linear combination of features that can make the output for us. In the example that we said, so here we have W0, W1 as a which is multiplied to X1, and X1 for us is like a feature, like so here what it intuitively means is like how important is feature X1, which is, for example, smoking, and how important is feature X2, which is the level of cholesterol, and so on, and what combination of these features can produce the output that we want, which is the level of the risk of heart disease. So, but how can we find this best linear combination of the features? So here it gets a little mathematical. You don't need to know the details. You just need to know the idea of how these models work. So the goal for us is to find the best linear combination of features. We can define a function which is called loss function, and we can aim to minimize the loss function or the error that we have in order to find the best linear combination of features, which means we want to find the best weights. In order to do that, so we have the actual output based on the data set we have, because it's a supervised learning problem and we know the ground truth. And we can also calculate the predicted value based on the weights that we start from. And based on these two values, we can calculate an error. And a combination of this error, doing some mathematical operations on this error, we can use this error to update our weights, to make our weights better so that we can finally find the best weights which can give us the output that we want in a linear regression problem. Like a simple calculation here can be, we have the actual weights, we have the predicted values using the formula that we had for the linear combination, and then we calculate the error, and our goal is to minimize this error to find the best model that fits our data and that can give us a good prediction. So this is the idea of the linear regression in general. And linear regression is used for regression. But what if we want to use the same idea for a classification problem? In this case, we use logistic regression. And the idea is somehow the same. The only difference is that for the output, when we are facing a classification problem, we don't want to predict a continuous value. What we want is most of the time a value between 0 and 1, which is the probability of that data belonging to the class that we have. So the same idea goes here, except that we use a sigmoid function, which is called an activation function, in order to get the output a value between 0 and 1. So again, the idea is the same. We just use an activation function that clips our data between the values that we want as the output for our model. An example for a logistic regression application in medicine is like predicting diabetic retinopathy. And logistic regression was used based on the medical test data to predict if the person has diabetic retinopathy or not. And it was shown to be effective. And again, you can go to the link later to read the paper on that. So we talked about linear regression and also logistic regression, which were used for regression problems and classification problems. But let's dive into a more complex setting where these models that we introduced are examples of a simple one-layer neural network. So the idea is that we have some input, which is called an input layer here. And we want to have, and we have some weights here, and we make a linear combination of these inputs, each with different weights, to produce the output. And sometimes before producing the output, we use an activation function like what we did in logistic regression to clip our data to the range that we want. And this is the idea of a perceptron, which is the smallest member of a neural network. So this is the idea of a simple neural network, and our goal is to learn the weights such that they can give us the output that we want. So as I said, we use different activation functions based on the output that we want and the range of the output that our data set has. And you can read more about these activation functions to get more acquainted with them. So I keep saying that the goal is to update the weights or to have the weights in a way that we have the best model. But how can we do that? So there is an algorithm for that. And again, you don't need to know every mathematical detail about it. Just the intuition of how it works and why it works is good. So our goal is to find the best weight. And what we usually do is we start from a random initialization. So our first set of weights are initialized randomly. And then based on the weights that we have, we calculate the predicted output and we compare it to the actual output that we have in the data set. And based on that, we can calculate loss. And based on that loss, we can move toward a better value for our weight. And we use an update rule for that, which is written here, and it's called backpropagation. And so we have our previous weight here, and we want to assign a new value to that. And we have the learning rate, and we have the loss for each feature, which is called the gradient in this case. And we update the weight in different iterations to finally get the weight that gives us the best model that fits our data. But it's not always that easy, because the algorithm that I talked about might sometimes get stuck in local minimum. So our goal is to find the minimum value for the loss function that we have chosen. But sometimes the loss function that we have might be more complex, and we might get stuck in a place where we don't want to be. So is there a way to solve that? Well, there is a way to solve this problem in the gradient descent algorithm, and that's adapting the learning rate to a value which is best for the problem that we're handling. So if the learning rate, so here, if I get back to this formula, learning rate is how much, how big of a step we want to take toward our goal. So if we take our steps too small, our algorithm might get to the point where it wants, but it might take a long time. And if we take steps too big, it might result in our algorithm to diverge, so that we cannot find the minimum part of the loss function that we want. So to solve this problem, there are some methods proposed. Again, it's just the intuition and the idea about why we want to minimize the loss function. And so for that, we use gradient descent. And sometimes there are some problems, and there are solutions to those problems, like using some optimizers, and some of them are listed here. So we can adapt the steps that we take based on the updates that we are making at each step, in order to reach to the point that we want, and avoid diverging and getting farther from the point that we aim to get to. So this is, so gradient descent and backpropagation is the core idea to neural networks. And this is basically the algorithm that neural networks work with. But there are also some design choices and details about neural networks that you might encounter when you're reading about neural networks. So there are some hyperparameters that we need to adjust based on the problem that we have, based on the data that we have, in order to have a good model which gives us good results. So learning rate is one of them that we talked about. Other things are rate decay, or the loss function that we choose that we want to minimize, or the number of sessions that we want to train our model based on our data, or how deep we want our network to be, or in each layer, how many perceptrons or units do we want to have for our computation. So these are design choices that indicate how our model works. So to summarize how neural networks work, we start from a random initialization of weights, and at each step, we have the input data. We calculate the output based on the input data that we have. And we, based on the predicted value and the actual value, we can calculate the value for loss. And based on that, we can perform backpropagation to update the weights, so that we can get to a better place. We can get to better weights that can improve our model. And so we continue this process until we have, we're at a good place where we don't need to change anymore. So here's a cool playground that you can visit later, which gives you some tools to play with. Like, you can choose how many layers you have, what data set you want to work with. And then you can press the start button, and you can see the process of the model being trained, and how it eventually gets to fit to the data that we have. So this is about neural networks in general. And Now let's talk about one type of neural networks, which is called convolutional neural networks, or CNNs. And the idea for CNNs, we can say that comes from a biological experiment done by Hubel and Wiesel. So they had a number of cats, and the cats were shown some visual stimuli, and the neurological activity in their brains were monitored, and there were some results from this experiment. So one thing that they found out is that there is a featural hierarchy. It means that in the visual system, the visual system starts by understanding and perceiving low-level features, and as it gets through the visual system, the features become more high-level. And the same behavior exists in convolutional neural networks. So in convolutional neural networks, as the network learns, it starts from low-level features and it goes to high-level features. So low-level features can be, is it a vertical line or is it a diagonal line? And high-level features can be, is it a face, or is it a chair, or anything else? So this experiment inspired the idea of CNNs. And another reason that this experiment is important is that the same filtering behavior happens in multiple receptive fields in the brain. So it means that when the cat was faced with the visual stimuli, if the line was vertical or if the line was horizontal, there were different receptive fields that reacted to that. The same thing goes on in convolutional neural networks. It means there are different filters in convolutional neural networks that learn different features in the picture that they face. So convolutional neural networks are suitable and well-designed for data that has spatiotemporal dependencies. So a picture can be an example of the data that has spatiotemporal dependencies, because different parts of the picture relate to each other, and this correlation is important, and it shouldn't be missed when we're working with neural networks. Convolutional neural networks can be used in a wide range of applications, such as classification, object detection, segmentation, and in medicine in particular, whenever we have types of data that have this spatiotemporal dependency, CNNs are a good choice. Like when we're working with ultrasound or MRI or X-ray, in different fields like radiology or pathology or dermatology, CNNs can be a good choice. Again, just intuitively, let's see how CNNs work. So we have an input for our CNN network, which is a picture, and we want to predict if it's X or O. So the output is a value which gives us the probability of this picture being X or this picture being O. There are different layers in a CNN network. The ones that I want to point out are convolution layer and pooling layer. So here in this case, in an example, in the picture, we have convolution, then we have ReLU, which is an activation function which adds nonlinearity to our data and our computation. And then in some layers, we have a pooling layer. And just to intuitively see how convolution works and how pooling works, so the input to our model is an image it means that it's a 2D array of different numbers, and each number indicates different levels of maybe different colors. And a convolution layer, so in a convolutional layer, we have a filter, and this filter goes through the picture that we have, and it's a piecewise multiplication, which is done in each iteration, and the output is a smaller matrix with different numbers based on the filter that we had. So the goal of the CNNs is finally to find a good filter that can give us the output that we want. But before that, as I said, there are many layers, there are many computations in different depths of CNNs. So one is convolution, the other is pooling. And again, when our input is a picture, it's a 2D array. And if we want to do pooling, there are different types of pooling. One is max pool. It goes through the picture, and in each score, it chooses the highest value, the maximum value, and it produces an output. So having all these layers together and doing all these computations, and in this example, having a fully connected layer, which is just a bunch of simple neural networks that we talked about. At the end, to produce our output, we can build models that can do amazing things, such as classification of data, or image segmentation, or other applications. An example for application of CNN networks for medicine can be classification, like classifying the image to see if the image indicates cancer or not, which is seen in this picture, or image segmentation, where we want to segment the image and find the parts that might be irregular or might be a tumor. These all are applications of convolutional neural networks. So here's a link that you can later go to, which contains some examples for CNN, and also for the models that we talked about today, such as decision trees and k-nearest neighbors and logistic regression. And I just want to go through them so quickly to just introduce you to how you can go through them and play with them. So here, so if you click on the link, you can go to the GitHub page, and if you download these files, or if you go to them, you can see them. But if you want to play with them, you can download them and then put them on Google Colab to work with them. So for the previous models that we talked about, like decision tree, k-nearest neighbor, logistic regression, as we said, these are classification problems. So we need a data set that is a classification task. For this example, we have a data set on heart attack possibility. You can read more about the data set in the link provided in here. It's a data set on Kaggle, which is a good source if you want to see data sets or see different problems in different areas, including medicine. So what you need to do is to first read the data set and do some pre-processing to prepare the data for your model. And then once you do that, you have the models and you can train your data on them, and then you can see how good they performed by maybe looking at their accuracy, so how accurate they were in predicting. So this is about the classification models, there's also a simple linear regression where you can see a line is fit to a bunch of data that are like a line. And for the CNN model, we have a classification task. We want to see if the person has pneumonia or not based on their chest X-ray image. You can find the data set and its details on Kaggle again. And I really advise you to visit Kaggle for seeing interesting data sets and problems. And so again, we need a bunch of pre-processing and preparing the data for our task. And after that, we need to build our model. So here in this example, we're using a pre-trained model, which is called MobileNet. And you can read more about it if you want. But having this model, then we train the model here in this cell. And after the model is trained, you can again check the accuracy, and you can also see how as the model starts to learn at the beginning, it's not in a good place, so it doesn't have a good accuracy, but as it goes, the accuracy gets better, and this is how the process of learning works in machine learning. So you can later visit these links to read more about these models and maybe see some code, some Python code, or different libraries that we use in Python for these tasks. So I want to come back to the big picture that we started with. So we want to talk about machine learning, and in machine learning, there are different problems like supervised, unsupervised, and reinforcement learning. And in supervised, we talked about classification and some different models like decision trees and k-nearest neighbors and CNNs and other things. Again, for regression, we talked about different models. And now let's briefly look at reinforcement learning, which is also an interesting field, and it has some applications in medicine. So the idea in reinforcement learning is that we model the problem with an agent and an environment, and the goal of the agent is to perform well in the environment it is in. So it receives the observation from the environment, which is called state, and based on the observation it receives, it does an action, and based on the action it does, it receives a reward which indicates how good the action was. And this constant interaction between the agent and the environment eventually leads to the agent learning about its environment and performing well. So you may have heard about reinforcement learning in games or robotics. And the interesting part is that it has its roots in psychology and neuroscience, but it is less used in medicine. And but there are many potentials, and I will talk about it later. And it's a good framework for when we want to do a sequential decision-making task. So here are some examples and links that you can go to see some examples of applications of reinforcement learning in medicine. One example is robotics. There are robots that are learned using reinforcement learning and trained using reinforcement learning. But there are some obstacles using reinforcement learning in the field of medicine because, as I said, trial and error and just constant interaction is the base part of reinforcement learning, and that might not be done in some medicine applications because medicine is a critical application. We also need a constant stream of data, so we might not have enough data in many cases, but still it's an interesting field with many applications also in medicine that you can, if you like, read more about. And that's it. Thank you. Any questions?
So you're getting a lot of praise.
Oh, thank you. I'm surprised. Thank you. I was super stressed, so I'm happy to hear that. Thank you very much.
Okay, thank you, Golnaz. I would like to actually emphasize on what people are saying over Zoom. You're an amazing teacher, so you might want to consider a career in teaching somehow. Okay, very quickly, one thing I was gonna show you before we end today is this resource. I don't know how I stumbled upon it, but I did a couple of days ago. So I'm just going to show this here. This is a website for learning Python from scratch, and they actually deliver because like this is it was pretty good when I looked at it. So it's futurecoder.io. Try and use this before they decide they don't want to do this for free, because some companies start with free and then at some point they're like, oh, well, you want the things you were using before, you have to pay this much per month, which again, we understand it's a business model, but anyways, so yeah, when you go on here and just start learning, like it actually starts with very basic Python. So if you have never coded before, this might be a good resource to look into. And it literally starts with type 1 + 2 and then see what happens on Python. So it's essentially just doing it on the go here. And then as you go through it, it just gives you feedback and all that stuff. I will share the link to this on Slack when I'm sharing the recording. So you'll see this there, but just wanted to show you very quickly before we do that. And I don't know if there are any questions here. Oh, they're asking for the attendance tracker. So I'm going to share that one here. Let's see. Okay. Yeah, so if you haven't done this in the beginning of the lecture, you can do so now. But otherwise, we will see all of you next week. This is our last one before the reading break, and then we'll resume after. We're going to be talking about ethics, privacy, and fairness in medical AI, which I'm really excited about. And Dr. Nidhi Hegde is going to give us that lecture. So yeah, thank you.